Today we will be designing a PCB for this layout using an STM32 F072 from this template, importing that KLE into KiCad using this KiCad KLE Placer Plugin by Zycra, and using footprints from Marbastlib. These links will be in the description. When you download and extract the zip of this repository, we will open KiCad and create a new project from template. We will navigate to that template once you've extracted it and hit select folder when you see meta but don't select meta. Here you'll be able to select the template, STM32 F072 CBT6 with USB-C. It's going to ask us where we want to save this new project. We'll save it here under Video PCB 2. My second take of this. Opening the schematic, we see it's already populated with the STM32, the USB port, ESD protection, a 500 milliamp fuse, 3.3 volt regulator, filter capacitors, a boot select and reset switch, and pin headers. The STM32 has a number of I/O pins, the USB data pins, and the labels for the boot and select switches. I/O pins labeled with FT or FTF are 5 volt tolerant. They still output 3.3 volt signals, but they are tolerant to 5 volt signals being put onto them. The timer peripherals here, there's timer 1 channels 1, 2, 3, and timer 2 channels 2, 3, and 4. Timer 2 is used by the SysTick, and so if you're using a timer peripheral, try to use timers 1 or timer 3 and not timer 2. I2C is available on a number of pins, especially on port 2. There's quite a few I2C or port B, quite a few I2C buses. UART is available on ports A and B in multiple locations, as well as SPI being available on both ports. Your SW debugs are on pins A13 and A14. If you're going to use these pins for other purposes, you may not be able to use the debug function, but just keep that in mind. Also, ports F and C are used for oscillators and for a wake-up interrupt. So if you can avoid using these, that would be advisable. The USB-C port, of course, has 5.1K resistors pulling the CC pins down to ground. That tells the upstream port that this is an upstream facing port running in legacy 2.0 mode. There's a 500 milliamp fuse attached to the rest of the components on the PCB. ESD protection for the USB lines also serves as reverse polarity with these through diodes. The 3.3 volt regulator has stabilizing capacitors on input and output, and a pull down resistor for, or a current limiting resistor on the boot select switch. Opening the PCB, just to look at what the template has to offer. We have what essentially is a black pill or some other development board. Alt-3 shows the 3D model. So we have these 20 pin headers. We're going to end up deleting these. And we also have our components like the STM, the reset switches, our fuse, our ESD chip, our 3.3 volt regulator, and the USB port, which does not have a 3D model in the default KiCad library. So any changes we want to make to the PCB as far as component like type or the number of components, or if we want to add or remove parts, we want to make those changes in the schematic. So let's delete the header since we won't be using them in our keyboard PCB. Control S to save, and then update PCB with changes made to schematic. It's also the F8 key, and all 3 of these boxes are checked. Hit update, and that deletes those headers. We can also remove the edge cuts by selecting the edge cuts in the right layers field hitting H to highlight just that layer, and then delete with a selection. And then press H again to cycle through. Take this whole assembly. We can select all items in the bottom right, and then just hit M to move it to the corner where we can have room to build our PCB here, and then we'll move these components back in when we need them. So let's do that. Let's import our components. So to do that, we're going to take a look at our keyboard layout editor layout. It has 11 switches in the top row, 10 on these two rows, and 8 or 6 on the bottom row, and then 3 keys off to the right side. If we go back to our schematic, we can place a sheet, add sheet, and we'll call this switches, and instead of untitled, we'll call it switches.KiCad schematic. Okay. And here we can go into the switches by double-clicking it. To go out of this page, you can click the root in the schematic hierarchy. If you don't have this column on the left-hand side, it is the bottom button on the left-hand side will open this column up. So going into our switches, we can add from that Marbastlib library our MX switch. Open Marbastlib, find MX solder. We're going to do a soldered PCB here today. And we're also going to add some diodes. So grab that D small symbol, rotate that, point it down, edit with E, and select diode SMD, and we'll do the 1, 2, 3. SOD 1, 2, 3. We can copy this 11 times for the top row, 10 for the middle two, and on the right side. So that's 12. So let's get rid of 1 of these. We'll grab 10 of these and put that in the middle. And we just need the 6 for the bottom row. I'm going to go ahead and space these out the way I think they're going to end up in the matrix. And then we also have these 3 switches that are kind of in between rows. Let's grab 3 switches here and their respective diodes and put them in between the rows off to the right hand side here. So the KLE Placer plugin, it reads from left to right, and you can read the notes on the GitHub README for that plugin. But what that essentially means is we want our keys in the schematic to be numbered as you read it left to right, and increasing. So that's 11, and then if you read the next row, well, this would be 12, but actually there's a key above it, so that should be 12. Then 13, 14, and that's 23 at that point, I think. So let's fill in schematic symbol reference estimators. We do the current sheet only. We will sort by the Y position as reading left to right. We will reset the existing annotations and use the first read number after 0. So start with 1. We'll annotate that. So now it reads 1 through 11, 12, 13 through 22, 23. It's perfect. All the switches have their respective diodes at the same number. That's important for the Placer plugin as well. Let's open our PCB, or save this, then open our PCB and update from schematic. And that loads in all of our diodes and switches. I'm going to keep the diodes over here. We're not going to do these right now, but let's grab switch 1 by selecting it, Alt-Tab, and then it's like highlighted, so you can just put your mouse over the center and hit M to move. Put that in the top left corner. We'll open our KLE Placer plugin. We'll select our JSON file from our downloads, and the designator is SW. We're not going to move our diodes right now, and we're just going to hit OK. That puts all the switches in the same places as they would be in the KLE. If we have a look here and here, right, everything here lines up with what it was on the right side. Now we are missing stabilizers for these two keys, so let's go add some stabilizers to our schematic. Back in the matrix, we can add stab. There's only a few things labeled stab in the KiCad libraries, so we can scroll, really scroll, my goodness. Stabilizer, there we go. Stabilizer. We'll grab a symbol for it. We'll edit that with E and assign the 2.25U and the 2.75U footprints. We'll save and update, and then that would line up here. We'll rotate it so that the smaller hole, which I know this yellow, so it looks like it's bigger, but it's just the black portion versus the blue. The smaller holes towards the edge, that's where the screw goes into the stab. So it's important to do that. And let's go ahead and edit our grid size to be some sort of divider of the 19.05 millimeter spacing of MX switches. So open my calculator here. We'll do 19.05. I like to do divided by 48, and it's pretty tight, but it gives us pretty good resolution to work with. So we'll just paste that into our X and Y and hit OK, and then we can use our user grid, which should be lined up with the switches. As long as we hit the user grid origin in the correct place. So if I place the grid origin, we put that in the center of the top left switch. So now if I go to make a drawing, it lines up with the grid, it lines up with the center of the switches, and it gives me a good space to put things right in between the middle of the 5-pin legs and the center of the switch. So let's do that now. Let's grab our diodes. We're going to put them on the bottom side. I'm going to hit F to flip them to the bottom. And grab diode 1 and move it with M, rotate it around. And I have my settings set that are rotate only does 45-degree increments, but yours are probably 90 degrees. We're going to place it here and then take it 2 notches down, which is like 0.7 measure, like 0.794 millimeters down from the center of the switch horizontally. And that gives us room to run a trace left to right without bumping into the center of the switch. So now that this one is placed, we can actually run the KLE Placer again, this time with the Move Diodes boxes checked and based on the first switch and diode. So the first switch and diode, diode 1 and switch 1, this layout will be copied to every switch, so all of the diodes will get placed. I've also moved our stabilizers because the stabilizers should have numbers lined up with the switch they're corresponding to, but we don't have that, so we can move our stabilizers back into the correct spot. I can select the stabilizer. Holding down a long time increases the number of things that are selected. Now you might have noticed some of these gaps, which is because the footprints are all 1U, while they're taking up the space of 0.75 or like 1.75U in this case, or 1.25U. So we can actually change that. In our schematic, we can run our footprint assignment tool. And in the places where you need a larger switch, like I know that we would want a 1.25U key on switch 13. We just go to switch 13 and we go to our PCM Marbastlib MX. And we'll grab that 1.25U switch. And likewise with the rest of these, you can change them if you want to. I'm going to opt not to for today, but that's just a little bit of, I hate the corner grabs, so small, Windows 11. Okay. So if I like update this, this is now 1.25U, it fills the gap. basically, which is nice. That way you can visually check. But I trust the plugin. So with this layout, we're fortunate enough that there's a gap that we can just take the entire assembly, flip it upside down so all the components are on the bottom, and then moving it by the center of the of the STM chip. That's the way all the routing can be centered on the STM chip. We can just place it in between these switches, and we're basically done with routing. Now, if we had to move something around, we can select just the STM and the buttons, and leave the power generation and the filters, leave that all here. We can just move this wherever it would fit. So here I might place it like between these space bars, right? And I can move those buttons out to the side, and then just delete the traces that don't work and rewire them. But yeah, this would be a pretty good location to put this chip. Perhaps near the shift keys. Oh, there's a really good spot here where there's no components that overlap anything. The buttons are right at the edge of the PCB, right? This would be a really good place to put it. But in our case, we have enough space. We don't have to. We'll just put that back. So this has got me thinking about edge cuts. Without anything defined, it actually doesn't look too bad. Of course, the USB port is not on the edge, so you can't really plug anything into it. But let's go on the edge cuts layer and make some drawings. In our 396 grid, we can start in the very corner and make a line in the edge cuts layer that goes all the way to the very edge here. And it goes down to the bottom, and if I'm off by one, I can fix it later. And then off to the corner, and then back up to the top. So let's fix these alignment issues. So this one needs to come just a bit in order to be square. So this line is now perfectly vertical. And then this needs to come just a bit down. I think just by one click of the grid. Perfect. So now, it still looks like a really messy rectangle, or a really big rectangle. But it's at least our rectangle and not some auto-generated layout. Now what I do like to do is inset these lines by 2 clicks. Just move it by the corner, 1, 2, 1, 2. This is on that 0.369 or 0.3969 grid that we completed earlier. Bring it in 2 clicks. Okay. Now this is going to throw an error because look, port outline is missing or malformed because they have like some overlaps. But it's okay. We're going to round the corners anyway. I like to make a round arc with a 2.3 millimeter radius and put that in every corner. Now, there are different ways of making rounded corners and making board outlines. This is just the workflow that I'm accustomed to. And then, if we highlight the edge cuts layer, we can take our edge cut and line it up with the edge of the corner, and it should snap into place with that little circle. We'll do that all 4 corners. Now if I look in the 3D viewer, it's going to be, if I don't miss, 4th corner. It's going to be rounded, it's going to be nice and approachable, it's going to look a nice keyboard PCB. So it looks like our USB port is kind of falling off the edge here. So we'll just, again, take the whole selection and we'll move it down until the line of our edge cut is past the ground mount points, the mount points for the USB port, but not past the edge of the USB port, which is this light blue line. Now our USB port should sit nicely. And in fact, I'm not a fan of not having a 3D model, so let's change that. If we edit our USB port and change the footprint from the default KiCad one to one found in the PCM Marbastlib various library, we'll grab the Type C31M12. It's the exact same symbol and the exact same footprint. So if I go to update from Schematic, well, nothing really changed, right? So like one of the silkscreen lines went away. But if I go into the 3D viewer, oh, now our port has a 3D model. And that's so nice to have when you're referencing the PCB 3D model to make a case design later. So the next thing to do is to connect all the diodes and switches. So let's connect every diode to their switch with a simple wire. And I'm using the net class width, which by default is 0.25 millimeters, which is a good small width that is, approachable, and most PCB fabricators are capable of making 0.25 millimeter traces. In fact, I wager to say all of them are. There's only a few switches here, so we should be able to blow through this pretty quickly. Now, I wish that the KiCad KLE Placer Plugin had the ability to copy not only the diode placement, but also the trace that connects the diode to the switch based on that pin 1 assignment. So basically, it would look at that, in theory, it would look at the switch, the diode, and the net name of the diode and switch that they share, the common net name, and it would copy whatever traces share that net name and the placement of the diode and the placement of the switch, and copy that across the whole layout from KLE. Of course, it doesn't do that right now, but I'll talk to the maker of the plugin and see if that can be added. I think it would be pretty nice not to have to click, I don't have to do it like 40 times here, but it might have to happen 100 times on a full-size board, so that can be annoying. So if I run our DRC right now, it's going to give us some errors about traces with unconnected ends, and that's all these traces that we deleted the socket, the pin headers from. It's not really an issue right now, but it's something to take note of. We will be deleting a lot of these traces in the router matrix. And then there are quite a few errors. Let's look at these errors. There are a few unconnected items. It looks like these aren't being picked up as connected, and neither are these. That's because the traces actually have the wrong name. So let's see if we can fix something about that. So it looks like these traces all have like DN, DP, while these have D minus and D plus. And this might be an issue with the template that will be fixed in a later version. And I believe it is, because here they're labeled DN and here they're labeled plus and minus. So if we delete this and replace it with plus and minus, save it and refresh. Now all the traces and paths have plus and minus. Okay, this is an issue with the template, and I will fix the template before I upload the video. Perfect. So yeah, if we run our DRC, those red arrows go away, and the only errors are board edge clearance violations between the edge and the hole of the stab. So in our 3D model, you can see that the hole of the stab is very close to the edge. It's not an issue when they're being produced, but it is closer than many fabricators like it to be. It's really not an issue. You just ream it out with a screwdriver if you have to. But this way, the PCB edge is tucked in tightly and away from the edge of the switch outlines, so that case design is easier to do. I'm pretty happy with this so far. So let's go back into our schematic and connect the matrix, and then connect the matrix to the controller. So in our matrix, we can add wires. I go to the left side, up and down, and then from the diodes, left and right. And that was a lot of directions in one sentence. So just copy what I do. Don't worry about left on over. What did you say? Anyway. Again, not very many rows and columns here, so we should be able to track through this pretty quickly. Of course, your switch matrix may be quite larger, and that's okay. Do note that there is a limit of how many pins you can use. This is a pretty soft limit, but the hard limit part of it is how many pins are on your microcontroller, right? So we're fortunate that with this microcontroller, if we go back to our root, we have all of port B and all of port A that we can access for matrix pins or peripherals or what have you. It's quite a few, right? So there's 16 here, and there's 14 or 14 because we were using 2 of them with D- and D+. So that's 30 pins, which is as many as like an RP2040, right? Of course, you don't have all the peripherals of an RP2040, or all the flash, or all the RAM, but you have just as many I/O that you can use. So you shouldn't be pressed for pin count, especially not with the template breaking out all the pins in nice, easy to reach spaces. So going back to our switches, let's make those rows. And here I connected this switch to the outer column with one trace. And essentially that means that these switches are electrically in the same column. That would be the backspace key and the QAZ on the left-hand side. So let's connect the rows here. And then likewise, I'm going to connect these rows like up to the switch. So essentially, these 3 switches are just, they're part of the matrix. They're just physically out there. So if I selected those switches and diodes, and I hit G to grab, I can literally just grab this whole column and move it over here. I have to grab the column as well, wouldn't I? There we go. I can grab the whole thing and just move it to the left, right? And that's where they would sit. Of course, they don't sit right there right now, but we'll get there. I like to have the schematic physically look like the keyboard, even if the wires need to go a little bit crazy. Let's add labels to these. Adding a label here on the right side, and then just calling it row 0. Let's grab that, put it where we can read it. And we'll copy and paste this to all the rows, and we'll rename them once we paste them. So we'll edit with E, that's row 1, 2, 3. And then we can also paste and put them on the columns here. This would be column 0. Copy and paste that across all of these. So we end up with, I think, 11 columns and 4 rows. Now these are the electrical columns and rows, and they do not have to match exactly the physical columns and rows. In fact, the electrical matrix, to be more efficient, can be as square as possible, even if your keyboard is super long, like an F-rowless TKL, right? That has like 18 columns, only 5 rows. It's a very wide aspect ratio. Where electrically, well, that's 18 columns and 18 pins, and 5 rows is another 5 pins, and that's 23 pins just for the matrix. That's a lot. Where if you halved that, you'd have 9 columns instead of 18, and you could double the rows if you like split it into half. So 5 and 9, so 10 and 9 is 19. So 23 down to 19 pins. You saved 4 pins there, and that's enough pins to add like RGB and an encoder. So that's enough pins to add like an OLED and a knob, right? Like that's when you're struggling for pins, you can always rearrange the matrix electrically, but keep the layout the same physically. That's what I'm trying to say. Anyway, we've got these labels made. Let's copy these labels over to our root page so that we can assign pins to these columns and rows when we know where to route them. So if we update from PCB, now we're going to see these air wires between the columns and the rows, and we can just use our traces to connect them. On the front layer, the red layer, we can connect our columns simply just top to bottom. Using the trace tool. And the trace tool and the line tool look pretty similar to me. Like this is a line and this is a trace, and I guess it has a zigzag, but sometimes I forget I'm in the line tool and I try to draw a column and it's just like, oh, there's a line that's not connected to anything. Or I'm in the trace tool and I'm like on a layer that takes lines and it doesn't do anything. I'm really confused. So get these traces down. And then this one we'll just take out a little horizontally like this. There we go. Now I'm switching the direction of the bend using the slash key. So right now it's going over and up, but if I wanted to go like up and over, I could like move the mouse around. It's kind of tedious. Or I can just hit slash, which is your slash question mark key, and that changes the direction of the bend. I find that pretty useful, especially when routing closer to the MCU. Oh, so this is going to intersect with the pole there. Now I have a setting on my KiCad here. I have a setting. If I go to preferences, interactive router settings. I have highlight collisions. You might have walk around selected. So let's see what that looks like. So this tries to place the component or tries to place the root without hitting the components. This is nice, but I feel like I have less control of where things go. Like if I wanted to connect it like that and manually deal with that later, I can't because it's going to route around things. And it just, anyway, I'm not a huge fan of this, so I just turn on highlight collisions and I manually see, oh, there's bright green. Don't do that. So we'll just take it around. All the columns here. We're almost done. The last column, just straight down. And then we're going to have to connect this column like over the USB port somehow, or like through the controller, right, to the other side. That's the only thing that's a little bit iffy about this solid block of pre-made, pre-routed thing is, well, you really are afraid to touch it, right? It's okay. Here, I'm going to try to put it over the USB port. That is really close to the PCB edge. So actually, I think we'll go between the USB port mounting points. And because the USB port is on the bottom and this is tracing on the top, the USB port will not be rubbing against the trace. And we'll see that in the 3D viewer here shortly. So let's look here in the 3D viewer what I mean by that. The USB port is on this side. If I flip the board around, the trace we just made is on the top side. So there is no physical contact between the port and the trace, so you have no worry about shorting out. Let's do the rows. So it's kind of bad practice to do this, but if you know for certain you're not going to use or move the diodes, you can just run the row all the way across. Just all the way across. All the way across. And if you can kind of tell, and you might be able to tell, I want to do most of my horizontal traces on the bottom side and most of my vertical traces on the top side, right? And that just makes it easy, so we don't have this issue where, oh, I want to run a trace horizontally on the top layer. Well, now I'm going to run into every single column trace, right? That's not going to work. Or if I want to move a signal from the top of the board down to the bottom, right? If I'm doing it on the bottom layer, I'm running into all these signal traces. Or if I do it on the top layer, okay, yeah, I'm going to run into a single pad, but I can get around that, right? So that's why we route horizontal on one side, vertical on the other. The last thing to connect are these two switches. Their rows go straight through all the components. But what we can do is bring that, like we said, down and around, and then bring it back up. But like we said just now, we don't want to put a big blue trace that goes down across all the I/O and bring it around. We'd actually want to bring it through a via. So to place a via, we'll just start making a trace and then hit V, V for via. And then that creates this kind of component, you can see here. Like brighten the screen a little bit. There we go. It's a little hole where the copper goes through the PCB. So we'll use that via to trace all the way down to the bottom of the PCB. And we'll grab that for this second row as well. Use a via and bring that all the way down to the bottom of the PCB. And here we can now go horizontally, right? Just to the outside here. And this one as well. Placing a via. And I actually don't like the spacing of that, so let's try that again. Perfect. And then this trace can just shoot right up to where it needs to go. Put down a via and connect it. Same over here, just place down a via and connect. So now this row trace, if I hit tilde or back quote, top left of your keyboard, that row trace, row 2, goes across all the switches and then jumps down and jumps back up to get that last one. Same for row 1 here. Row 3 you could just go across because, well, there's nothing stopping it. Nothing in the way. So the next thing to do is to grab a bunch of I/O and just shove it over to the matrix columns and rows. And we're going to do that by connecting our rows and columns to these labels here. These can come off with Control-C, Control-V, and I can like connect A0 to column 1 or column, whatever it is. So let's go to our PCB and just find the pins we want to use kind of in line with the columns that are existing. So do we have, what was it, 12 columns? No, 11 columns and 4 rows, so 15 pins. And the rows are pretty easy to get to. They're on that bottom layer. So I can like just hook up, boom, there's a row, right? And then just find a pin, there's a row, right? But the columns we actually want to bring closer to the MCU. And to do that, I say MCU, my microcontroller unit. Yeah. To do that, we're going to create what is called a bus. Now, buses usually are bad design. Electrically, they're not great. But we can do it in this case because it's a very slow signal. This matrix scanning happens, it might happen 1,000 or 5,000 times per second, but 5,000 times per second electrically is not very fast. So we can create these big horizontal traces that all line up on top of each other. We'll start just putting one trace down, and then we'll grab the next one. And I'm pulling this just out of the column on the switch. We're just going to place them, stack them up right here on the grid. And then we're going to skip one, and the next one, the next one, next one, next one. Let's see how many we can fit. And there's 3. There's 4. 5. 6. 7. 8. And just 2 more, 9 and 10. And we'll get that 11th one from the top. 9. And last one, 10. The 11th column here is, you can either grab it from the bottom, the right side, or the left side. Then we'll get it from the left side. We'll use one of these left side pins to do that. And then the rows. So being that there are already 10 pins on this side, which is, I think coincidentally, exactly how many pins are available to use that aren't F or C. Actually, this side has 20 pins. Just 20, straight up 20 I/O we could use. So we can connect all of our rows and columns to one side of the controller, which is going to be super nice just from an aesthetic standpoint. So let's start lining things up. I'm going to delete a bunch of these traces, and then we'll put them back pretty soon. So I know that row 3 is going to be our bottom one. And then we'll do row 2, and then we'll do the columns 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. We'll do row 1. We'll do row 0, and then we'll do column 10 last. That's from bottom to top. And if we look at these pin names, it's A0, A1, A2, A3, A4, A5, A6, A7, B0, 1, 2, 10, 11. We've got so many pins we could use that are already right here. So let's just delete the traces that are already existing. Select them. Be careful not to select too much. If you want to, you can just hit tracks in the selection filter in the bottom right. And this is a good starting point. It brings all the traces out where they're accessible. And we can start connecting these traces to different parts of the matrix. So row 3, let's just grab it, and we'll grab it a little bit like this, and we'll put that on A0. So let's just set the trace down for a second. Go over to our schematic. Row 3, we want A0, so we'll just grab our A0 label and put it on row 3. So I just lined up those square boxes and it connects them. And if I wanted to, I could make a little wire between the two. Maybe that's a little bit more readable, so let's do that. So if I update from the schematic, A0 connects to row 3. And then row 2 is the next one, and that's going to be A1. Grab A1, put it on row 2, put a little wire, update, and then we can just run this trace right up there. Perfect. Now for the next one, it's column 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. That's the most of our columns, and it's really easy to remember what order they're in. So let's do this in a big old batch. We'll grab the next 10 pins, A2, 3, 4, 5, 6, 7. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's A2 through A7. B0, 1, 2, B10. So we'll grab A2 through A7. Copy and paste. We can, that'll be columns 9. There we go. So B0, B1, B2, and B10. B0, B1, B2, and B10. And that is our next bit there. We can flip that, right click, mirror horizontal. And we can just connect all those to the columns. There's column 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Update. Perfect. So we can just start hooking the matrix up to the pins. And I like the way these kind of come out sideways, so we'll continue that pattern just by changing our grid to 0.25 millimeters and making our grid origin the center of the chip. Right? So we place the center of the chip on both grids. 2.5 millimeters is the grid that this project, right, the template was made in. So we can continue the nice even spacing. So here we'll just continue that even spacing. And we'll hook it all up nice and pretty and delete the extra bits. Goes here. Last two. And then we just have a few more traces. I did have some whoopsies here with the spacing, so let's try to fix those. And it looks like we may not be able to fix them all, just because, well, it's a really sharp corner. We'll just bring it over. Okay, so that's the majority of our bus complete. The next pin that we can use is B11. Now we'll grab row 1. So we'll just grab B11. We can flip that horizontally. That goes on row 1. Bring that down on the grid and then just straight over. This does look really weird with a sharp angle, so let's just round that off just a little bit. There we go. It looks a little better, I think. The last thing is column 10 and row 0. We just need 2 pins here. So this is B12 and this will be B13. So row 0 will be B12. Yep. We'll flip that horizontally. And then column 10 will be B13. Just put that there. Update that PCB again. And connect it up. Here we can just go around the switch like we did before. And then get rid of this like ugly corner. Just retrace it, and then if you need to, just select those sections and delete them. That's basically it. I think we are doing pretty good for time. Can't really tell. There we are, 48 minutes. So yeah, 48 minutes to go from KLE to PCB. The last thing we need to do is clean up all the unused tracks and vias. So before we do that, let's run our DRC. So we should see only those 4 errors for the board edge, because we don't have any traces that overlap anything. And we have plenty of warnings, and these are mostly to do with tracks that have unconnected ends. And if we get past that, a bunch of silkscreen stuff with the diodes. So let's clear all of that up. So the unconnected ends, oh, the last thing I did not check was if there's any in the error sections, any unconnected items, and there aren't. There are tracks with unconnected ends, but they don't go anywhere. There's no second part to that track. We didn't assign VBus to anything else in our schematic. So if we go to Tools and clean up tracks and vias, we want to delete track. Let's go through these options. We'll delete tracks that connect different nets. That's a short, right? If we had like ground and VCC accidentally connected, then selecting this would delete those tracks so that we didn't have a short anymore. If there are vias that are on top of existing vias, or vias that are in pads or in holes, then this will delete that, or rather, not in pads, just in holes. If there are vias that only collect one layer of copper, which is kind of hard to do, honestly, we'll delete those. If there are tracks that butt up, like one comes horizontally and connects to the other one, just in a straight line, that will turn them into one single track. These will delete all those tracks with unconnected ends, and this will delete any tiny tracks that may exist. Like there's a track that goes from this vertical line diagonally to the center of this one, but when we check this box, it will delete those tracks as well. So to show you, there is a track inside this pad, right? If we run our tools, clean up tracks and vias, and we update the PCB, now there is no longer a track inside this pad. I cannot select one, right? So everything's cleaned up. All of the extraneous connections we did not use are deleted. So if we run our DRC again, half of those warnings are gone, which is great. So let's fix the other 80 warnings, which are all about silk screens. We've got lines, we've got text that are all being overlapped with this hole, right? So this hole overlaps all of that text. So if we go to our selection filter and select text, and then select the bottom silk screen and hit H, you'll see all the text associated on that bottom silk screen. We can just select all the diodes and hit delete. We don't really care which diode is which, because they're all identical. And we all know that all the diodes are going to be between switches, and there aren't diodes anywhere else. So there's really no point in referencing that on the PCB itself. This also gives it a much cleaner look, in my opinion, in the 3D view, without all the random text being cut off by holes. So if we do our DRC one more time, we'll see that pretty much all the warnings are gone. Now we just have these lines. And the lines, well, I don't want to go and edit the footprints, but that line is being deleted by the hole. And if we have 40 of those warnings, well, that kind of makes sense, doesn't it? Because if we go back to our schematic in our switches, well, we have 40 switches. So if we have 40 diodes whose lines are being cut off by the hole, meaning that all 40 of those warnings, we don't really care. You know, we can ignore them safely. And the same for these 4 errors about the board edge clearance. There's the edge, and then there's the pad, right? And that's that screw hole for the stabilizers. Like we've said before, that's not going to be an issue. So here we have it. We have a board. It's a PCB with the layout that we wanted. On the bottom here, we have our STM controller we got from the template, the boot and reset switches that we got from the template. You know, and of course, you always feel free to move these parts around, right? You can move the boot switch to be somewhere else if it's like in the way. And you can take the USB port and the ESD. So J1, U2, R1, R2, and the USB port. And then C8. These components, these 5 components, and the USB port, that's our USB circuit, right? That's our ESD protection, our power, our fuses, our filtering, our main filtering cap, or like our first filtering cap. These capacitors, C9 and C10, are the regulator, or the voltage regulator. So this group of 3 can be placed away somewhere else if you needed to. C2, C3, C4, C5, C6, C7, C1, those all belong to the STM. So that is your main bulk filter cap for the STM. Then the C3 through C7 are your smaller filter caps, or I guess not filter, but decoupling capacitors. C1 is your reset pull-up, or like reset stabilization capacitor. And then R3 and R4 are the pull downs for your boot select button. And the reset button kind of lives on its own. It can be anywhere. It just needs to have access to that reset trace and a ground pad. And same for the boot button. It can be anywhere. It just has to have access to that boot select trace, or I guess whatever comes off the resistors, and then a 3.3 volt pad. So yeah, there we have it. The PCB is complete. We can add silk screen, we can add graphics, we can change the edge cuts up if we want to. This will be a functional PCB. Now, one thing that people love to do, and I like to do it too, is add a ground fill. And this, you know, with the template already having big ground traces, like this trace here is is our ground net, right? So we have our ground going through the connector, and then this big red trace carries ground all throughout the whole thing. So it carries ground to the reset switch, it carries ground to the ground star that's within the STM. It carries ground to all of the capacitors around the filtering capacitors and decoupling capacitors, right? So we don't need a ground fill, but sometimes it might be useful, especially if you have like encoders or OLEDs or other peripherals that need a ground connection. You don't have to run the ground trace if the ground fill connects it. So let's go back to our copper layer. We'll add the filled zone button, Control-Shift-Z. For everyone using keyboard shortcuts, I should be. We'll do it on both layers. We'll do it on the ground net, and I'm just going to make a box around the whole thing. It doesn't have to be a perfect box, it could be a sloppy box. There's our box. If we edit it with E, we can do some settings here. Clearances of 1/4 millimeter and 1/2 millimeter. Those are pretty good. I mean, they're standard and they're pretty good. So the fill can be hashed. It can be solid. We can round the corners if we had the fill within the PCB itself, not just around the whole thing. We could round the corners. It looked pretty cool. So let's do a hash pattern. Let's do it on, I don't know, give us a crazy angle, 20 degrees. And let's have the hatches, the copper traces, be like 1.5 millimeters wide with 2 millimeter gaps. And let's just see how that turns out. We hit B for build fills, builds the zones. Well, that looks pretty sweet. So if we look in the 3D viewer, yeah, that looks awesome. And anywhere that is filled with this hatching pattern has a ground connection. So there's only one spot on our PCB that we cannot access ground, and that's right here. So let's add a via, just straight up a via. I don't have to add a trace, just a via. And click in that like blank spot and edit that and assign it a ground net. Just like that. So now when we hit B to refill the zones, look at that. So that's now filled with ground copper. Now we have ground everywhere, which looks really nice. So I'd consider this a finished PCB. Congratulations if you followed along. If you didn't follow along and just wanted to learn about this template, well, there's a link in the description for how to download it and have fun using it. The template itself is a dev board, so if you want to just order that, oh shoot, you're just about done. All right, so this PCB is done. Let's order it. So if I go to the Fabrication toolkit and just click it, it creates a folder with a zip file, which has our Gerbers, a positions CSV, which has the position of every part, and then a BOM, which is a bill of materials. So let's open that bill of materials, open it with whatever Office program, like Excel. You can open it with Notepad if you want to, but Excel usually is the best one. Sorry, did I lose audio? No. I'll open that up with LibreOffice Calc, because that's what I have on my computer. We'll just import that CSV, and we will change the column width so it's not going off the screen. There we go. So the tool did try to fill in some of the part numbers, but we probably know that some of them are wrong. Because the 10 microfarad, the 1 microfarad, and the 100 nanofarad capacitors probably aren't all the same part numbers. Now, I have curated a list of parts which are on JLC, which are basic parts, resistors, capacitors, and others. And we're actually, yeah, we're good. Okay, so it's not a complete list. There are way more parts on JLC than what's in this list, but we're just going to use this list to populate our BOM here. So our switch is a TL3342. In our others, in the switches, we can find the 3L TL3342, grab that part number. It's green. It's the basic part, which is great. Our capacitors are 0402 footprint, 100 nanofarad. There's our 0402. We'll find our 100 nanofarad here. And there's like 2 of them, so we'll just grab the first one, C1525. The 1 UF, it's 0402, 1 microfarad, so grab that. 10 microfarad, and this is in the 0603 footprint. So we're just going to grab one of these. Our diodes are SOD 123. I think it's right here. Let's get it. Our fuse, 500 milliamp fuse in 1206 package. So 500 milliamp, 1206, grab that. It's an orange part, it's extended, so we're going to have to pay a small fee to order that on JLC PCB, which is okay, like $3. Our HRO Type C port, I think, is here, Type C in 12. 5.1K resistors in the 0402 footprint. Here we are. Our stabilizer, there's no part associated with that at JLC. We have to order those stabilizers on Amazon or something like that. So delete those rows. In fact, we can delete the whole row. Same for the switches. And then we'll grab the STM. So that's in the controllers, STM, grab that part. The ESD protection, that's in the PRTR, we'll grab that part. And then our regulator, voltage regulator, so it is here, the SOD 23. And that's our BOM. It's filled out. We'll just use the text CSV format. And there's our bill of materials complete. So we can go now to like jlcpcb.com. And of course, there we go. Looks like either I don't have internet or JLC PCB is down right now, but you can use those 3 files, the zip, the positions, and the BOM to order your PCB from JLC PCB. Anyway, that's all I have for you today. It was nice designing with you again, and we'll finish that TKL video series at some point, I promise. All right, thanks.